Welcome to STEM Ventures. This is my segment, Rocket Science 101. And so this is a little event that we do about every month. And we have different tutors come and talk about things that they like or that they're passionate about. And for me, that's rockets. So, without further ado, I'm a Valencia grad. I transferred to UCF last January. And I currently am pursuing a bachelor's in aerospace engineering. I did my prereqs here for my engineering, and then I moved along. And my ultimate goal is to, well, be an astronaut, if you couldn't have guessed. But until then, I also want to get my PhD in planetary science. So, all right, so, and let me just, this is a prop, but this is like a real rocket that I'm building. So there's something called the National Association of Rocketry. And there's 3 levels to it based on like the height and what actually goes inside the rocket, right? So like if you make your own GPS system, things like that. So this is my level 1 rocket. It's not anywhere near done. It's about halfway there. But I brought it because I wanted to use it as a prop for some of the things we're going to be talking about. Because the rocket equation is a little aggressive, I'm not going to lie, but I think I boiled it down to something that's simple enough that everyone can understand, even if you're just in like developmental math. So hopefully you guys have fun with this, all right? So today's lesson, we're going to be learning the rocket equation, the infamous rocket equation, and that is essentially was derived using classical mechanics, right? So things like Newton's second law, Newton's third law, kinematic equations, and also the conservation of momentum. So we'll go over all of those, and then we'll tie back into the rocket equation and how it works out. Classical mechanics is, if you don't know, it basically describes the motions of bodies under the influences of a system of forces, right? So the physical concepts employed in the mathematical models were invented by Isaac Newton and some other scientists around the early 17th century. We use it to predict how objects move in the future and in the past if we know the present state, right, of either its velocity, its position, etc., etc. We won't go too far into that. So we're going to start off a little bit backwards. We're going to start with Newton's third law, actually. So for every action, there is an equal and opposite reaction. And how many of you are aware of Newton's laws of motion, right? Okay, perfect. So there's actually 3. The first one is you sum all the forces and you set it equal to 0, which means that the body is not moving. So you have something like hanging or like a street light that's just kind of like a traffic light that's just kind of sitting there, right? It's in equilibrium. It's not accelerating any. The second law we'll go over, I think it's in a couple of slides, but that means that the body is accelerating. So we take all of our forces, we add them up, and we set them equal to mass times acceleration. And the third, of course, is for every action, there's an equal and opposite reaction. And how that plays out in rocketry, one of the most fundamental terms. Let me see. So while they're doing that, I'll skip ahead to the rocket part, right? So this is in the next slide. So for every action, there's an equal and opposite reaction, right? And what I mean by opposite is a different direction. So if a rocket is moving up, right, towards the air in the positive z-axis, right, there's an equal and opposite force that is going down in the opposite direction. And we notate that with a negative sign. So that's kind of the essentials on which we're going to build everything else from. Now the speed at which the rocket launches has to do with the exhaust, with the change in mass that's coming out of the rocket engine, right? So, fun fact, rockets are about 90% fuel. So this outer shell and aluminum casing in some cases only comprise about 10% of the rocket, right? So if you think about that, that's a lot of fuel that's inside here that what does it do when rockets ignite, right? They burn, so they eject that fuel out through the tail. And so that velocity that it's shooting forward is actually also executing that through the exhaust chamber, right? Or through the engine. And so that change in mass times that velocity has to be equal to the change in mass times the velocity as it moves forward. Yeah. Testing? There we go. All right. So, let's skip ahead. So we just covered that. All right, so now on to Newton's second law. So, is this rocket accelerating after ignition? Yes, right? So now we're not going to use Newton's first law, that's in equilibrium, right, equal to 0. It is actually accelerating at some rate. And so, what we like to do in physics is we try to understand what's going on, all the forces that are acting on a body and how they relate to its velocity, its mass, its time, the distance it goes, the height it travels, right? Anything like that. And so there are a couple things as to what a force is. Does anybody know what a force is? Does anybody have an example maybe? Energy? That's close. So energy is something that we use with momentum, or they entail certain parts, certain variables of kinematics. So like kinetic energy is equal to 1/2 mass times velocity squared. So that's something a little different. Forces are things that, like friction or the tension in a rope, a force, right? There's also a force due to gravity. And just to be clear, gravity is not a force. Tell all my students that. It's not a force. Weight is a force. Because would you agree that the gravity on Earth is different than the gravity on the moon? And what about the gravity on Mars, right? So gravity is different. It's relative to whatever celestial body you're on or wherever you are in the universe, right? So that's why gravity is not a force, but weight is a force. So if we take that gravity of whatever planet we're on and we multiply it by the mass of whatever body whatever body that you are taking into account, right? That is equal to the weight force. And that one's important in rocketry and, you know, when we're standing, right? Because we put this rocket back up, right? We have a weight force that is pointing where? Up or down? How many say up? Raise your hand. Right, exactly. So if we're just thinking about the rocket, so there's 2 forces on this rocket, and that's the next button click. So who can name the 2 forces? Anybody? I gave you one. One's a weight force. Can anybody else guess the other one? What was that? The normal? Yeah, very good. So the normal actually comes into play. That was a great answer too. Good job. So friction would come into account if I was rolling something. So I'm going to put this down. So friction would come into account if I'm pushing a body across the surface, right? There's an opposing force that's going to eventually slow me down, right? So that's friction. But the normal force comes into account when you have anything on a surface, right? But that's when an object is not accelerating. So when an object is accelerating, normal force doesn't come into play. So the second force is the force of thrust. And I know I kind of cheated because it's not on the sheet. But there can be other forces as well, right? So these are just a couple examples. The force due to gravitational forces, which would be the force weight, right? You've got your normal force, which happens to any body that's standing on a surface, right? Like me on this concrete right now. There's a normal force that goes straight up and is equal and opposite to my weight force. And that's how they cancel out, right? And I'm not accelerating if I'm just standing still like that. But with rockets, they overcome that acceleration, they overcome that weight force, right? Of that mass times gravity. And they do that with the thrust of a rocket engine. So I keep hitting my computer, I'm sorry, I forget. Can you guys see the screen or is there a glare on it right now? No? You can see it? Okay, perfect. A little bit of a glare for me, so maybe I'll step forward a little bit. All right, so how that comes into play is now back to the actual physics of it, right? I say for Newton's first, second, and third law, all we do is we add the forces, right? And we either set them equal to 0, equal to mass times acceleration, or equal and opposite of itself, correct? So for Newton's second law, we want to overcome that weight force. And what we do is we set it equal to mass times acceleration. Well, what do we set equal to? We set equal to the sum of all the forces acting on the body. And like I said, if the rocket is just sitting there at the launch pad, the only forces that are acting on it are the weight force and the force of thrust that's about to happen with it. So we would go ahead and write a positive force of thrust, right, which is going in the upward direction, and a negative weight force because it's going down towards the center of the Earth. Now that's fine and dandy, but what do we do next? How do we relate anything else to this equation? How do we solve for the acceleration? How do we solve for how fast this rocket goes, the velocity, right? Well, that's where kinematic equations come in. And so these are some fun charts that you'll learn to love if you take physics. You can't hate them because they don't go away. But they're explicit of kinematic equations. And kinematic equations are just a subfield of those classical mechanics we were talking about. And it describes the motion of points, bodies, and system of bodies, without considering the forces that cause them to move. So if I want to find the velocity of something, but I don't know the force acting on it, I can use kinematic equations, right? And there are four different variables that we can relate to it. We have a displacement in either the X or the Y direction. We have time, and we also can have acceleration. And by relating these position, velocity, acceleration graphs shown on here, right, we can solve for the acceleration of a rocket. And have you all taken algebra, maybe? Anybody? So you know what was it, oh, they're gonna get mad at me, I used to be a math tutor. What is it, the point slope formula? Point slope formula? Y equals mx plus b. So got it, all right. So I'm physics, we don't really focus on the math too much, we just have a bunch of variables. I'm just kidding, the math is a very important part of it. So you guys all remember the point slope form, right? The y2 minus y1 over x2 minus x1. Well, that's what we call in physics or in math as well, a derivative, right? It's a derivative of something. And that would give you like a straight line across, right? From one point to the other. So if you take the point slope of the position, you get the speed or the velocity. If you take the point slope of the velocity, you also get the acceleration. So knowing this, we can set the acceleration equal to v2 minus v1 with respect to time now, because we want to know the total distance or speed it's going over a period of time. So that's all it is, it's nothing crazy. So when I say, when you see this little symbol, the delta V, that just means the change from final to initial velocity, right? So now we know what the A is, right? But what comes after A? We have the velocity now, right? So we want to find the speed of a rocket. We want to know how fast it can go. And we can do that now that we know that acceleration is equal to the change in V over the change in T. But we don't know V, and that's where the conservation of momentum comes into play. So let's recap real quick. There's only 4 things: Newton's third law, Newton's second law, kinematics, and conservation of momentum, right? And we talked about conservation of momentum earlier. It's equal to mass times velocity, right? But, well, that's momentum. But the conservation of momentum states that the initial momentum must equal the final momentum. So the mass times velocity of this rocket, when it's sitting on the pad, needs to equal the mass times velocity at any point after it is launched. And that's not including air resistance or anything like that. So this isn't a perfect world with no air, okay? So what we're gonna do, I think it's on the next slide, is I'm gonna run through the math for you guys, and you're gonna see how the mass is related to the velocity of a rocket. So let's just recap real quick. The conservation of momentum means initial mass times velocity has to equal final mass times velocity, right? And that's the case with anything. With billiard balls, well, you guys saw. It's the case with billiard balls, anything like that. You can actually calculate the velocity of a pool ball, even if it's hit 2 or 3 after you hit the first one into it. And that's all because of the conservation of momentum. So if you have 1 billiard ball and you hit 2, let me put this down for a second. So if you have 1 billiard ball and you hit 2, and they split off into different directions, you can actually calculate the velocity of each of these 2 things. because if you have the velocity of the first one. Because initial velocity has to equal that final velocity, right? MV initial has to equal MV final. So here's the fun part. I did the math for you guys, don't worry. It took me all morning. I'm not lying. So here we go. So here's the thing about the rocket though. It gets a little crazy because not only do you have the rocket, right? Remember I said that you have fuel inside this rocket that is being ejected at a certain rate, right? At a certain rate of change. And that's the crazy part. So when we're taking into account this system, the initial is going to be the mass of the system, right? So the mass of the rocket outer shell plus the mass of the fuel. So we'll pretend that, we'll call that MS, the mass of the system, right? So the mass of the system initial times the velocity initial, which we don't know yet, we will solve for. Plus, what is eventually going to split off is going to be that mass of the exhaust plume, right? Times the velocity of that exhaust plume. And so we'll be able to calculate that as well. And so when we go through this process, just keep that in mind. So there's a lot of variables that come into play. And what we can do here is if we have the mass of the system and its initial velocity, and the mass of the system and its final velocity, if I want to solve for the mass of the system, can't I just move this final over here? Can I not just move this final over here? And let's see if I can write it out for you guys. Okay, so I know this is a little mathy, but basically if I have the mass of a system times its initial velocity, and the same variable over here, the mass of the system times the V final, can I not just subtract this chunk and put it on this side of the equation? Is that acceptable? Yeah? Right? So say I'm solving for x. Can I just move it over if it's part of the same variable? Right? So that's all we're doing in physics. So we have ms, and that would make it V final minus V initial is equal to the mass times velocity of the exhaust plume. And so that's all this math is doing. So that's what all this math is. It's an over-exaggerated form of what you've learned in algebra with your x's and your y's. All right, testing 1, 2, 3, loud and clear. There we go. So when we do that, what we end up getting is that the mass of the system, the negative mass of the system, it ends up being negative y. Can anybody tell me which law? A negative force is equal to the same force. Which one is that? Close, the third. We started with the third. So for every force, for every action, there's an equal and opposite reaction, right? And so that's what ends up happening here. The math checks out. Go figure, right? Who knew? So what we end up getting is the negative mass of the system times the change in velocity is equal to the change in mass, the mass that is being exerted out of the rocket plume, times the velocity of it. And so it's pretty neat how it all works out. And now, let's put it all together. So if we said that Newton's third law was the sum of the forces equals mass times ma, right? And we said how many forces are acting on a rocket as it is standing up?
2.
How many? 2, very good. The force of weight and the force of thrust. So we set that equal to mass times acceleration, and that was the first thing we did. Second thing we did was, okay, well, we had to solve for acceleration. We used our kinematic equations to find that acceleration is also equal to the change in velocity over the change in time, right? So if we plug that little change in V into the A of our first equation, we get this bad boy. Force of thrust minus force of weight is equal to the mass times change in velocity. And then we use conservation of momentum to solve for that velocity, right? To solve for that. But what we actually get is a mass times velocity. And isn't that the same that we have right here in this equation? Right? There's an m times change of v right here, right? So all we can do is take this data right here, or these variables right here, that are equal to mass of the system times the change in velocity of the system, and just plug it back into this equation. And you'll see that because that is the red part here plugged into this black equation here. right? And so we're almost done. So this is for all the future engineers out there, right, and physicists and people who actually want to go into this, or even if you want to understand it. So this takes a little bit of calculus. So I just put it up on the screen for you guys. But if you take that equation that we just saw and you integrate it, right, you can end up solving for the velocity. And the velocity is equal to a logarithmic function of the initial mass over the final mass, which is equal to the final velocity minus the initial velocity. And so that's it, guys. That's the ideal rocket equation. And it was only 4 steps, so it wasn't even that crazy. Now, we're not getting into fuel types or specific impulse today. Maybe another time. I hope not. I'm just kidding. I would really like that. So yeah, so now it's time for you to to launch your own rockets, right? And so I have some Alka-Seltzer and some water. And so we'll do that in just a moment. But the cool part about this is you can actually calculate the velocity at which it's shooting off at. So these are not going to be airborne for that long, maybe like 1 to 3 seconds, depending on like the ratio of how you do it. And you'll have a whole packet to yourself, so if you want to do a couple launches, you're more than welcome to. So we have some whiteboards here, and the equation you're going to use is V equals AT. So does anybody know what acceleration due to gravity is? There's a number for it. 9.8. Very good. Very good. So all you're going to do to solve for the velocity at which your rocket was launched at is you're going to do 9.8 times whatever time you get. So we have some stopwatches here, and the directions are on the screen. And I was messing around with these a little bit today, and the directions are pretty good, right? So they say, open the film canister, right here, and fill it like 1/3 with water, and then put a half of Alka-Seltzer tablet in. So these packages come with 2, so just break one in half, put it in, and you don't have to run away from it. It takes a couple seconds, maybe 4 to 7 to launch, so don't worry, it won't splash all over you. But make sure you close that lid really tight. So you pour the water, drop the half of Alka-Seltzer in, and then you're gonna place it on the ground and get your stopwatch ready. You can work in teams, so like you're not rushing for anything. And write down that time, and then see if you can calculate your velocity for me, okay? Do you guys have any questions before we do the experiment part? None? Okay. All right, how many of you want to be engineers or go into STEM? 1, 2, 3, 4, 5. There's the girl. Girl power. All right, very cool. So if you guys have any questions, let me know, and then you can just come up here and start getting your items, okay? Thank you so much. Have a good day.
We got 2 seconds in the air.
Oh, that's smart. Okay.
Whoa!
Oh, was not ready for that. That was really high. Nice job. Okay, what was your ratio?
Who, me?
Yeah, you.
I don't know, I just guessed it.
So like 1 tablet, 2?
2 tablets and then 2 full tablets.
I did 1 full tablet and then the quarter of the water, and that's how I was able to get it very high.
So that's because the gas bubbles were able to have more volume to expand.
Okay.
And then when it was finally ready to explode, there was a bunch of gas inside. So
Yeah.
it just shot straight up.
Yeah. Just try to be careful not to act in a water so it doesn't not go quickly.
Yeah, I'm going nowhere near space.
I ain't going nowhere near.
Yeah, it worked. Partially.
That was so nice. Alright. What's your passion for this space?
Yeah. I like space and like also like helping people out, so it's kind of like
Yeah.
And I volunteer at a hospital, so I kind of like doing that too.
I mean, honestly, you should just get your bachelor's. All right. In aerospace, and then you, because like, then you can go to med school and do whatever.
Yeah.
Well, you can go to med school with a bachelor's in aerospace?
I think you have to take a couple more credits, like a couple more like biology and anatomy classes. But yeah, I'm pretty sure. Talk to your advisor.
That's pretty nice.
Yeah, I'm taking
Yeah.
a one right now.
You could also
Okay.
do like geology too, so you
yeah.
like space rocks.
So that's what I love.
That's
so,
what my
Be
sister wants
a
to do
prospector
really
of
bad.
the
Yes,
21st century.
it's so
Gonna go
cool.
mine
So
asteroids.
Yeah, exactly. So I love regolith, which is like the term for loose soil and dirt on other like celestial bodies.
Yeah.
And I just love it. Like, it's so fascinating because I love the whole planetary science part of things. I used to think I wanted to be like an astrophysicist.
Oh.
And so I learned like what it was.
Is it true that Mars' regolith is like radioactive glass? Lightly looking?
Lightly, not a huge portion of it, but it is true that it's a little glassy. So the moon is a little more glassy and jagged. So if you think about it, the moon has like no atmosphere, right? So that means there's no erosion, there's no wind, there's nothing for like the rocks to smooth out. So
Do you
we
think
actually-
the moon is hollow inside?
Huh?
You don't think so?
So we can actually use
That's
UV
what the
and
dinosaurs
infrared
are.
spectrometers to like
I don't know.
shoot UV and infrared like waves at the surface.
Okay.
And it can tell you how deep something is. And so UV rays actually penetrate a little bit deeper than infrared. But that's how we're able to tell like the mineralogical composition of like the soil on Mars or the soil on the moon, where the water ice is on the moon and things like that. And so I currently study the effects of radiation on the moon because we want to prove how the ice forms, how the ice layers form, right? So we take a specific chemical compound, we take aluminous silicates, which are not only like 50% of Earth's crust, but they're also predominant throughout the solar system. And we put basically with and without water, and we bombard it with different forms of radiation, and we see how those molecular bonds break apart and then reform.
Okay.
And so we like literally prove how the water and the moon forms. So there's different ways that you can prove things like that in a lab. It's just yeah, definitely not hollow. But did you guys know? Okay, so I learned this morning on my new favorite podcast, Walk About the Galaxy. It's based out of UCF, and UCF is actually #1 in planetary science in the nation, if your sister didn't know. So lead like planetary scientists like who run UCF like have that podcast. But anyways, so Earth has a new moon right now. So
Yeah, I heard about that.
Did you hear about
It's
that?
like car sized?
So it's actually a little bit, I think it's like 0.94 of a meter. So a little over 2 feet. But yeah, it actually accidentally got stuck in our orbit and it'll be here for a little while.
And it's
so
budgeted out in March or
So when you say it'll be here for a little while,
Yeah.
is it gonna, the orbit's gonna decay and it's gonna fall into our atmosphere?
I don't know. I didn't get that far in the
It
podcast.
could, but it
so,
wouldn't cause any.
So yeah, I think that might be the case because if it's doing anything else, I don't think it'll have enough
Can't get
like
back out.
it won't have enough potential to like slingshot back out if it already got stuck in our orbit. So yeah, probably. And then I think detrimental meteors are like what, like anything bigger than like 3 meters that hit the surface and everything's done. But
Yep.
we should be
I always
fine.
wonder, why is the moon moving away instead of moving closer to us like
In
any
what
other?
sense?
I'm gonna head out.
It's like, why is
Alright,
the moon not
okay. Oh, you want me
falling?
to step back?
Why is the moon
yeah.
not getting closer to us as time goes on and it loses rotational energy? Like, why isn't it going to hit Earth?
You know what? I haven't looked too far into it. I think it's just because of the mass of it. It's stuck in an orbit that's far enough. So you know, if we put things like, I think it may eventually over time, but I think at that point it'll be like hundreds of millions of years later, just because the mass of it is so big.
Yeah.
Yeah.
I'll send you the videos.
I think
if you want.
the stars, the sun is.
Sounds good. All right, I gotta go.
We'll check
Hopefully
them
we'll
out
have
on that.
less.
I'll see
Yeah.
ya. Thank you so much.
You're welcome. Cool. Well, this has been so fun. Thank you guys for coming out.